Okay, we're going to start gases. Remember, chapter 9 and 10 are together on the test. So we have states of matter and gases together. No, the test isn't tomorrow. When? Yeah, not next week, but the week after. Yeah. No, 10 and 11. Oh, yeah, 10. Right? 10 is states of matter.
Okay. So 10 and
11.
Not 9. No 9. 9 is not in this.
9 is not in the test.
Okay, that's okay.
I misspoke. The other honors class has 9 and 10 together. You guys have 10 and 11 together. Okay, so to start with gases, we're going to look at pressure, the units of pressure, and then we're going to look at the Dalton's law today, and then we'll be finished, and we'll talk about gas laws tomorrow. So pressure. Pressure is a force per unit area. And the units for force are newtons. And so when you have a newton per area, it would be meters squared. That is called a Pascal. And so Pascal is actually the SI unit for pressure. But we will use ATM a lot. That's probably what you will see the most is ATM. So if the same force applied to a smaller area gives greater pressure. And so if you have the same force applied to a smaller area, so let's say you have 2 different blocks on your leg. One's a big, like what size would that be? 5 inches by 5 inch block on one side. And then you have a ½ inch by ½ inch block, and you put the same force on it. Which one would you feel the most pressure with? ½ inch, right? Because you're putting more force in a little area, so it would feel heavier. The force isn't spread out as far around. So if you have a smaller area with the same force, you feel more pressure. Well, but the surface area that object would be touching would be the same. The example of I've seen is if you have a large ball and you drop it into some clay versus a smaller ball, but it has the same mass, but it's a smaller ball. Then you drop it in the same clay. The smaller ball will go deeper into the clay because it has more pressure. Because it's able to apply more pressure on the clay. Right. It's like you're concentrating that weight in one area versus spreading it out. When you measure pressure, atmospheric pressure, you're actually measuring the pressure, the force, the air molecules above you all the way to the top of the atmosphere is applying down on you. And so it's really talking about this column of air above you and what is the pressure that it's applying to you. And we measure that with a barometer. So the barometer is a column of mercury with a well of mercury exposed to the atmosphere. This next slide has a picture. So here's the well of mercury, and it's open, so the air is able to push down on this mercury. The only place that mercury has to go is up this vacuum tube, so there's no air in here. It's going to be pushed up. The more pressure pushes down, the higher the mercury rises up, and you take the difference in height, and then that is what your pressure would be. So this one's 76 centimeters. What? I don't know why mercury. That's just what they have always used. So when you see mmHg for a pressure unit, and then it's millimeters mercury. When you check your tires, what units do you use? PSI. That's pounds per square inch. So it's pounds, which is a force, per square inch is an area, force per area. That's wind, I think. So let's go back to those units. So at sea level, the pressure is 760 millimeters mercury. We will a lot of the time use ATM, so it gives you some conversions for ATM. 1 ATM is sea level, and that's equal to 760 millimeters mercury. It's also equal to 1.01325 times 10 to the fifth, or 101,325 pascals. That would be the SI unit. There's also kilopascals. So if you have 101,000 pascals, that would be only 101 kilopascals. And then torr, 1 torr is equal to 1 millimeter mercury. And so one important point is standard temperature and pressure, STP. And you will see problems that say, at STP, what is the volume of this gas or something? So it's when it says STP, you have to automatically know that means 1 ATM and 0 degrees Celsius. So let's do some unit conversions. The average atmospheric pressure in Denver, Colorado is 0.83 ATM. Express this in millimeters mercury and pascals. So if you can't really see that. Let's change that to yellow. So if I have 0.3 or 0.83 ATM, and I want to change it to millimeters mercury, how do I do that? Units down here need to be ATM, and then we can go to millimeters mercury. Do you guys remember from that previous slide what the conversion was? 760. So 1 ATM is equal to 760 millimeters mercury. That's all you have to do. And simple unit conversion. If I want to change that to pascals, instead of going to millimeters mercury here, I want to change that to pascals. Do you guys remember what the pascal was? 101,325. No, I will give you those equivalents when you have a quiz or test or something. It was 1.01325 times 10 to the fifth. So instead of doing the times 10 to the fifth, 101,325. Should have been like 94,099.75 or something, if I remember right. 84,000. Oops. Okay, the pressure outside a jet plane flying at high altitude. So if you're high altitude, you have less air pushing down on you, so the atmospheric pressure falls considerably. Therefore, the air inside the cabin must be pressurized to protect passengers. What is the pressure in atmospheres in the cabin if the barometer reading is 688 millimeters mercury? So they don't bring it quite up to standard. 760. 1 ATM is 760. So we want to change it to atmosphere. So this time we'll have 760 on the bottom to 1 ATM. It's going to be point something. Oh, 5. ATM. So questions on unit conversion? Oh, that's just my answer, yeah. Okay. The last thing today is Dalton's law of partial pressure. So a lot of times you don't have a sample that is just one gas. It's usually a mixture of gases. And so we use what are called partial pressures to indicate the pressure of just that individual gas within the sample. And so Dalton's law is that the total pressure is equal to the sum of the individual ones. So, and usually we don't call them like gas 1, gas 2, we actually have oxygen gas. So if I want to find P1, pressure of oxygen gas, it would be like PO2 plus maybe hydrogen gas plus water vapor. So you're going to look at, it will actually show you which gas it is usually instead of just calling it P1. But you're just summing them up. And then also, so it might give you a total, it might give you all but one, and you have to solve for the other. You just subtract, or you'd add these together to get the total. But sometimes we were given percentages, like in this problem. So calculate the partial pressure in millimeters mercury exerted by the 4 main gases in air, nitrogen, oxygen, argon, and carbon dioxide at STP. Ooh, what does that mean? Standard temperature and pressure. So what is standard pressure? 1 atm. So that is the mixture. So that's the total is equal to 1 atm. Their abundance by volume is 78.08%, 20.95%, 0.934%, and 0.035% respectively. So if I want to find the partial pressure of just nitrogen, I would do what? Well, 78% is nitrogen, 78.08%, and we know the total is 1. So you want to change this to a decimal, 0.7808%, and not one of these other ones. Because when they're given in list form and it tells us respectively, that means it's in order of what they listed. Yeah. Times the total would be 1 atm. That's all you gotta do. Now this is easy because our total was 1, right? Not your total will not always be 1, but it's yep. But that's the process you would do. It would give you the next problem we have is not at standard. So what would the pressure of oxygen gas be? Mm-hmm. What about argon? 0.0034. And carbon dioxide? Whoops. Oops, I need units. There we go. Okay, so this next one actually doesn't give us percentages or it's not the ATM. But if we have, okay, so we have halothane is a non-inflammable, non-explosive, and non-irritating gas that's commonly used in inhalation anesthetics. Suppose you mix 15 grams of that halothane with 23.5 grams of oxygen gas. The total pressure of the mixture is 855, so we know that. I'll write that up here. 855 millimeters mercury. What's the partial pressure of each gas? Can I find the percentage of each gas? If I have a mixture and I want to know how much of that is actually oxygen, I'd take the mass of the oxygen and divide by the total to get a percentage, right? So we need, if we do oxygen, 23.5 over 38.5 times 100 gives you what percent? Add these two numbers together. 61%? Okay. So if I want to find the pressure of oxygen, let's see, I'll do that down here, would be 0.61 times what? What? Yep, the total pressure, so 855. And so that is 21. So we need to find halothane also. There's two ways we can do that. We can do this whole process again, just switching out 23.5 and we want to use 15. Or what should the total... So based on... No. No, you can pack those. The total pressure should equal the two pressures added together. So we can take, to find halothane, we can take 855 minus the 521 to give us halothane's partial pressure is 333.45. Oh, I forgot the mm. Questions on that? Collection of water is just a specific type of using Dalton's law, because a lot of times when you collect gases, you bubble it through water. Let's look. So here that's bubbling, it's evaporating the gas, it's coming through and bubbling through water, and it's going to fill this jar and push the water down out. But when you collect this, it has that gas and water vapor in it, so you just have to subtract out water vapor. That's all it's going to do. So we have a total pressure of 762 millimeters mercury here, and the water vapor is 22.4 millimeters mercury. Now, the partial pressure of water will change based on temperature, and there's a chart in your book, I don't know what page it's on, but it would have like temperature in one column and then give you the partial pressure of water vapor in the next. So all you have to do is subtract it out. So for this problem, you take 762 minus 22.4, and that would give you the pressure of oxygen. So it's just a specific kind of Dalton's law. Yeah. Okay, that's all the notes for today.